So this is a circuit symbol for a capacitor. A capacitor is in some way similar to an inductor, with also an element that can store energy. And for an ideal capacitor, it doesn't dissipate power, only energy power, and extract power from capacitor, but itself cannot dissipate power.
So it only store the power.
Yeah. So this is a relationship of is carried and is merged across the terminals. So it's this way. And this is similar with this inductor. This and this is similar, but the relationship is opposite. Way. Means this is way and this is carried. So for this valve, C is the capacitance of the capacitor. It is unit in farad. It's F. So this is very big, very big. So we usually use N mu F. Mu F, mu means right? And also we can use PF. Means very small. So this is the capacity of the capacitor. And from this differential equation, so again, one, voltage cannot change instantaneously through the terminals of the capacitor, because if we have a gap, means the difference is infinity, right? If the voltage at a time, if have a gap, means at this time equals infinity, right? So this means the current through into the capacitor is infinity. That's important, right? So vertical change is infinity. So this means a voltage jump would produce infinity current and basically permeability. And the second, if the voltage across the terminals is constant, means the temperature is zero. Yes. Right. So the current is zero. The current is zero means an open circuit. Right. So we get this. A capacitor behaves as an open circuit in the presence of a constant voltage of a DC socket. And in a DC socket, the capacitor looks like open socket. So this cutting express the current with the voltage. So how is the voltage with the current? Or voltage part of the current? So from this, we get times the differential time, both sides. So we get this, right? And this, and this.
Going to be simplified.
With an element. So we get this. So for this way, we separate the voltage and the current. So integrate both sides, we get this. If the capacitance of the capacitor is constant, so we can remove this to the outside. And so this is the variable is voltage. So if we analyze at the interval from t0 to t, so this voltage is from Vt0 to Vt. And this, the interval, the variable, differential variable is time t. So this is from t0 to t. So we get this equation. And so this, how is this? How is this? This is x, right? And so equals x and right. And so this is equals so if we times C, right? So we get this Vt equals this is this. So this is voltage in terms of the current. We get this. Do you remember the current in terms of the voltage for an inductor?
Yes.
You know?
It's 1/8.
Yeah. It's similar. This we neck. This is capacitor.
It's going to be just
this way. Wow. And for an inductor,
Integral Vt t plus Itc.
and it's two similar. That,
Yes.
but the vertex and the current must be change its pace.
Yes.
So usually or in general, T0 is taken as 0. So this expression we can write in this way. This way. So because we have learned the relationship for an inductor, so the relationship between the capacitors, voltage and the current, is similar. So next we find the power and the energy in the capacitor. So we take a positive sign configuration this way. So this is current, and this is voltage, and power P equals V times I. So we get this. This expression or this expression. Anyway, I calculate the power. So if we know the current through the capacitor, we can use this way to calculate. If we know the voltage, so we can use this way. Maybe this way, the calculation may be simple. This may be difficult. So, how is the power? How is the energy? So, because from this equation, so we can get this, and we take integrals both sides. We get. So this is the next result for the energy. So it's only
1/2
he said only to this voltage, right? And its capacitor. So this is this is a stored energy. Can store energy. In this way, we can store energy, and this store device may be useful for in physical, because if we use an inductor as an store energy device, you must sustain the current, right? So you must sustain the current, right? And so the current flow in circle. But because the inductor, basically real inductor, has resistance, and the wire also has resistance. So the stored energy can be smaller and smaller. But if you use a capacitor for a store energy device, so if you sustain the voltage and it is needed current, so this you can take an open circuit. So there is no current and no resistance dissipated. So the energy
can be stored.
in theory, and it can store a long time. This cannot store a long time because there is
The current
resistance to dissipate energy. So this way may be better than inductor. So this is the energy, this is power, and voltage and current. So next we see an example 5.4. This example in our page 146. The voltage part described as this expression. The following equations is impressed accrued terminals of a 0.5 mF capacitor. So C is C equals 0.5 times
times
million.
about 6.
Yeah. So in this C equals 0.5.
Times 10 plus 6.
Right. And they say A, derive the expression for the capacitor carrying power and energy. So we know the voltage, but we need to calculate current I, power P, and energy W. B, get the voltage, current, power, energy for waveforms as function of time. Line after the plus voltage. So the same way, number 503. And C, specify the interval of time when energy is being stored within the capacitor. And D, specify the interval of time when energy is being delivered by the capacitor. And the next, E, evaluate the integrals. And command on their significance. So, this is voltage, right? And the first we must to calculate the current, right? So the current, how is the current?
Is a C dV over dt.
The current means we must like this.
Yes.
So, Z is long, V is long, but the V we separate three parts. 1, 0 for t smaller than 0.
Yes.
And the second part, 4 times t. So, in this way, I equals, we can separate for three parts. 1, 0, right? And this part is differential is 4. 4 times 6. So this means 4, 6. Right, 4, 6.
Yes.
Say, how is 6?
C is 0.5.
And say we get so this is 2 times and unit n. So we can write this way. And the third, how is different?
Yeah, it's going to be 2.
That's the difference.
But it is just
4 times firstly, this 4 we can remove this outside. Right?
yes.
So 4 right. We can remove 4 outside. And this and this is serve, right? Serve. Do you remember the mathematics calculus? Yeah, but so this is 4 times, but this x not t. So this x, how is x? X equals, right? And so in this way, so this we must to calculate this difference for t, not for x. So we must simplify. So x is this. X, the difference is,
X squared.
how is the difference? Right. X, this, this differential, is negative 1. So we get this must be times 6, right? This means this, and this we times 6. So we get minus 2, right?
Yes. Oh, that's it's
And this mu r. Okay, maybe the calculation and maybe a little difficult. But if you mathematics about the calculus is very good, so this calculation may be not so difficult.
but the integration we will start it, but not yet. Integration.
Okay, the legs may be simple. P, power, equals weight times I. So we get 3 parts. 0 times 0, 0. And 4 times t times 2, we get 8 times t. This is weight, and this is mu A. So we get mu W. And this times 6. So we get minus 8. And this. So we must this is also mu W. And we get weight I T, and then the next we must to calculate energy. W. W only divided by weight. Correct. Because the energy right. So this 0 and this 4 times t and times 4t. So 16 times t times t. But there is
It's divided by
0.5 and c 0.5. So we get 4 times t times t. And so this way we get this. So the 4 waveform we get 4 functions naturally plot for waveforms. This is vertical. So we cut the waveform with MATLAB. So if you maybe use MATLAB earlier, maybe the calculation may be very easy. And this is carried, and is unit mu A. And this is weight. And so this is power in green marks. And this is mu W. And the next is the energy. and this is in mu J, u J. Okay, this example we code the four waveforms and say how to say specify the interval of time when energy is being stored in the capacitor. So how to
On
so
on one is storing the energy.
one thing is unmeasured is to say the power is positive or negative. Positive means energy stored in the capacitor. So in this way, this is 0, right?
Yes.
So from 0 to 1,
One, yes.
power is positive,
Yes.
and others power is negative. So in this way, left side power is stored into the capacitor,
Absolutely.
and right side
It's
power
derived.
is taken from.
The capacitor to this.
So another way we can
Look energy.
look the energy waveform. Increasing means stored into the capacitor. Decreasing means extracted from the power. So T equals 1 is a separate line.
Yes.
So, and this time interval energy is stored in the capacitor. And with the characteristics of storing energy, 1, P is positive, another an increasing energy cost. And other helps, and is being delivered by the capacitor. So the characteristics P is negative and or decreasing and current. And the next E, we need to evaluate the integrals. 1, this, because the time is t in an interval 0 to 1, so the power p is a times t, right? Note this, right? So we take this into the equation, right? So this integrals may be easy, and so we get 4 mu joule. And next, we must calculate this. This because t is at the interval 1 to infinity. So this power is this expression. So we get this into the quotient. We get this integral, calculate this integral may be difficult, more difficult. So we get this, and we get this minus 4. This is positive 4. This is negative 4. So this equal in 1A. So that means the energy stored in the capacitor all extracted. And next, stored in the capacitor is 0, right? Or minus 4 equals 0. So this represents the energy stored in the capacitor during this time interval. And this represents the energy retained by the capacitor extracted. The voltage applied to the capacitor retains to 0 as time increases without limit. So the voltage because as T and T approach to 0, right? So T also equals 0, right? Because that is this way. So this approach 0. So W approach 0. So what applied to the capacitor returns to 0 as time increases and without limit. So the energy retained by this ideal capacitor must equal the energy stored. So means this must equal this. That exact side. Right. Okay, another example. Example 5.5. This in our page 148. Okay. And uncharged 0.2 μF capacitor is driven by a triangular current path. The current path is described by this expression. So we need to derive the expression of the capacitor voltage and power and energy. So we need to explain another 3 expressions, right? And B, plot IVPW for waveforms versus T. And C, why does the voltage remain on the capacitor after current returns to 0? So, next, we divide the other 3 expressions, right? Because the current expression is long, and so this is long. And next, we derive other 3 equations. And this with according to time, we separate the 4 parts. Right. This part is very simple because I is 0, V is 0, P is 0, and W is 0. The first part. And the second part means I equals this, right? So this is carried and vertex. Vertex, we must calculate this. This is I0. And so this may be simpler. This may be simpler. And so power V times I. Yeah. So we get this. And the next, energy. Energy as this way. Only by this vertical. So we get this. So I the relation T and this T times T and T times T times T and T times T times T times T. So we get the part 2, and part 3. So this we must calculate at the end, at the part of the end. When t equals 20 mu s, we get v equals 1. Because this is the initial value for the next part. Right? Because this v0, this v0, and this is the next part v t0, right? And the third part, firstly, I is not, and v is 5. This 5 means that why we calculate this, because we need this value for the next part. And so we get this expression. And so next we calculate power, right? And is unit W. And the next we calculate the energy. Energy we use this way to calculate. And for the first part, the first part is this. And so this, we mean T equals 40 mu into this, we get V equals T. Interesting. And this current is 0. So P is 0. And the energy, so use this way to calculate. Okay, the other 3 expressions. So we next we plot the 4 waveform. Let's say this is the triangle carried pulse, and this is vertical. The next vertical. T. It's a constant. And power. I times weight. We get this. And the next. So from the four waveform, at what time interval the energy is stored into the capacitor?
Yes, it's served and dissipated.
Because the power is always positive. So the capacitor is always storing energy.
It's not delivering. It's only
No, it's ready. And this time over 40 mu s, the power is zero.
Yes,
Means the capacitor stores energy and not stored and not extracted and waste energy constant. So the energy waveform is an increasing curve, not decreasing.
So Laoshi, on 40 it can even be like an open circuit.
No big.
Open circuit on 40.
40.
Yes.
Yeah. And 40. The stir is not in the capacitor. Not outside, not inside.
So it can be even open circuit.
So this energy is stored in the capacitor. This is a stored energy device. Yes, this way. Yes. But this is in ideal capacitor. If a real capacitor, maybe the energy may be moves slowly. Okay, this is the whole waveform. And next, C. Because the power is always positive for the duration of the current path, it means energy is continuously stored in the capacitor. When the current returns to zero, the stored energy is trapped. Okay? When the current returns to zero, the stored energy is trapped because the idea of no means of dissipating energy. Thus, the voltage remains on the capacitor for I returns to zero. Okay? Now, the next section, 5.3, it is till next time. Okay? Today, that is all.